Let's begin with indexing techniques. So in indexing technique, what we understand is you have a file, a table, anything, whatever, how to retrieve it very effectively from your computer or from your memory, right? We know that your data is stored in your computer. So the question, how to do effectively? To understand that, first of all, you should know the computer architecture, otherwise memory architecture. So how your memory is organized. If you don't know that, so how can you improve it, right? So if you want to improve that, first of all, you learn existing techniques. That means how this data actually stored and how that can be retrieved. So for that, we are going to machine details. So first of all, this memory structure. So your memory is generally typically divided into three parts. We know that, of course: main memory, secondary memory, tertiary memory. Quickly we will see positives and negatives of each one. The among them, which is this main memory, is very important and fastest. So since it is electronic device, so typically the data rates, example, some data is in main memory. If you want to access it and you want to copy that data from main memory to CPU registers, generally why we do it is, the reason we want to do addition of some two values. For that, let's say your data is in main memory, then we have to move them to CPU registers, because only CPU registers are connected to that circuits, right? Such a way your machine is designed. If that is the case, then we have to move that values from main memory to CPU registers. So that takes after a nanosecond of time. So typically this is the data transfer rates from main memory to CPU registers. Even we'll see that later, like about secondary memory. Now what is secondary memory? Which is example is disk, right? So the problem with disk is it's electromechanical device. That means there is lot of mechanical activity. Because of that, it takes lot of time to take the data, otherwise to give the data. So that's why whenever you store your data in secondary memory, it takes lot of time. Typically the data rates are milliseconds. Of course we will see into details, and at this moment let's assume that it is milliseconds. So tertiary memory is usually tapes. So the structure of tertiary memory can be imagined like this, and whenever you want to store the data, the problem is it won't support direct access. You want to store the data, example, at this moment here, then this is already filled. Let's say data is like this: 1 2 3 4 5. Then you want to insert data here, then we have to start here and we have to search for the position which is empty. We can't directly know where the empty space is, and that's the reason. That means you can't address this tape. That means, example, the address of this position like 1000 or something. Directly I can't jump to 1000 without going through this entire thing. So that is compulsory. So that is a major bottleneck of tertiary memory. That's why typically it takes milliseconds, but thousands of milliseconds, otherwise 10,000 millisecond typically. So finally you tell me, if really you want fastest memory possible, then which one you prefer? Main memory. But the disadvantage of main memory, whenever you switch off your computer, then all your data will be lost. That means main memory is volatile. That's a problem. Then what to do? Then definitely we should use secondary memory, otherwise tertiary memory for, I can say, for second alternative. That means whenever power goes off, your data should be permanent. For that, for alternative, we should use extra memory, that is secondary memory, otherwise tertiary. So among this secondary memory and tertiary memory, if you see the data rates, millisecond is better than 10,000 millisecond, right? So I can say that I can use secondary memory. And second thing, this secondary memory supports direct access. Example, you want to store some data in a particular disk address. This is your secondary memory, let's say disk, and you want to store the data at particular disk address. The disk address, let's say. Then directly we can come to this point and we can do it. For that, we don't require to see this entire data. That means we don't require to depend on other data which is stored. So that's why I can say that main memory and secondary memory generally support direct access. Whenever I know the address, directly I will jump to that position and I write it. So it takes, of course, milliseconds, because there is a some electronic and mechanical movements we will see. Because of that, it takes lot of time. Now among these two, definitely I prefer secondary memory. Then why we have to study tertiary memory, sir? Can we remove this entire tertiary memory from our subjects, otherwise from our literature? No, the reason, sometimes we use tertiary memory. Example I will tell you. Tertiary memory is, one positive point is it is cheapest. That means so we can have terabytes of data for after all 500 rupees, otherwise 50 rupees I can say. So 1 terabyte of data you can store with a cost of 50 rupees. So exact cost I don't know, but just assume like that. But whereas to store terabytes of data, that means if you want to purchase a hard disk of terabyte or something, you have to invest some 1000 rupees or 500, at least 2000 rupees. That's why bulk data if you have, example, so these banking people like State Bank of India, ICICI, so these people maintain lot of data, right? They will have thousands, crores of customers, and every day they do activities, transactions, they remember everything. For that you need, I mean, thousands of terabytes of data, right? We want to store it. But example, let's say one user has done some transaction long back, like 5 years back. Still this SBI says that I remember it, let's say. Then, but that transaction no one requires generally, very rarely, maybe yearly once, otherwise 5 years once, this user may want to see this transaction. That means very rarely he want to refer such data. For that what I do is, such all the data I keep in tertiary memory, and regular data I keep in secondary memory because it's costly, right? Otherwise all that data I can, everything, whether it is junk or not, everything I can store in secondary memory, I don't have any problem. But it takes, it needs some money, right? So investment wise it is better. And what you do is, there will be in every organization there will be some data which is very rare to use. That means yearly once, otherwise 5 years once. If you have such kind of data, then why to store that in secondary memory, and why to waste your money? Rather than that, move all that such data to tertiary memory. In that way, tertiary memory is also important. So now in regular basis, like in a daily basis, which memory we use? Main memory and secondary memory. What is the problem with main memory? It is costly, one thing. Second one, it is volatile. That's a problem. That's why we need some main memory and secondary memory in a regular basis, right? Now, from now onwards, you remember your data is going to be stored in secondary memory always. Then only it will be permanent, right? Now, see this story. This is your computer CPU, and these are all CPU registers. Why CPU registers are required? CPU registers are specially designed so that they are connected to your adder circuit, subtractor circuit, let's say multiplication circuit, everything. So if you want to do that kind of arithmetic, then registers are used, right? They are very fast. I can say faster than main memory. Now usually what people do is, whenever they want to add something like x comma y, then I assume that, let's say, already x comma y in main memory, then this x will be transferred here and y will be transferred to CPU registers. Later they will be connected to adder circuit. Such a way your machine is designed. Now, so but how to, sir, why in the early morning when I switch on the computer, how can I have data x comma y here? So it is not there, we have to move it. So before that it is definitely in secondary memory. We know that it is permanent storage. If you store x comma y once, that will be permanent. Now we'll see disk controller. So what this disk controller does is, so this is the hard disk and this is a small processor you can imagine, and whenever CPU orders this disk controller with some data and address, so the disk controller is going to store the data in this secondary, I mean this disk, because this controller knows how to access this secondary memory. In that way, all the problems and all the everything related to this disk are separated from the CPU. Now CPU never bother about this disk details, so disk controller will take care of that. So for that, because of that you get lot of advantages. Now CPU never worry about, otherwise never wait about this disk, right? Simply whenever you have data, let's say D1 and address A1, simply give it to disk controller. The communication will be like this. My dear disk controller, CPU is saying that, my dear disk controller, please store this data in address number 1. We know that you have address 1. Then immediately disk controller says that, okay, you do your work, Mr. CPU, don't bother about it, I will do it and you take care of your things. Once it is done, then I will give some signal to you. So somehow disk controller gives the signal to CPU that this work is done. So once disk controller gets the data and address, it will go to the particular address, because disk controller knows where is address number 1. It will go there and it store the data. After that it will give signal to CPU, then CPU understands that work is done. Now we will see actually how this hard disk is arranged and how disk controller is going to maintain this disk. First of all, you should know the details about this your hard disk. So I am going to teach very important details which are required for understanding indexing. So this is your disk. Generally your disk will have multiple plates. So plate number 1, plate number 2, plate number 3. So every plate is attached to, see here, one IO head, otherwise disk head. This black color thing is disk head. So every disk has a head. The purpose of head is just read the data. Okay. Now your disk contains a parameter called track. So this is called track. Now this is another track. Every plate will have some tracks which are concentrated circles, I can say. Now here you can see one more parameter, that is this red color thing, which is nothing but sector. So every track is divided into parts. So each such part is called sector. So these are all the disk details. Now cylinder, what is cylinder, I will tell you. Example, let's say you have a track, right? This is track, this is track. Now if you take all the corresponding points in every track, in every plate, then if you connect them, so logically we will form a cylinder. We'll see what is the meaning of cylinder and how that cylinder is important for us. First of all, how data will be stored in this kind of mechanism we will see. What happens actually is, whenever you have data and you will give that to disk controller, right? So disk controller knows where is the address. Okay, so somehow your disk controller changes that address to these details, like you have plate number, right? So example, your typical address, whatever you have, so that will be like this: plate number 1 and something, track number 1 and some position in the track number 1, sector number 20, in that way. So finally your address will be divided into 3 parts: plate number, track number, sector number. And your disk controller, somehow it will go to that plate and track and sector and it will write the data. So first of all, so how this real plate, otherwise correct plate and correct track, correct sector will be identified, I will tell you. So actually this plate is generally rotatable, that means it can be rotated, and your IO head also movable. So what happens is, example, let's say this is track number 2 and this is track number 1. Initially, let's say your IO head is resting on track number 1, let's say, and the designers know how to send a IO head or disk head from track number 1 to track number 2, and they know distance calculations. Example, the distance between T1 and T2 is something like 1 millimeter. Then they know all the details, like this IO movement, head movement, right? This is a mechanical movement. So first of all, I will tell you what are the things will happen. So whenever you want to store some data here, like in track number 2, then your IO head somehow, so who will instruct, we'll see later. So IO head slowly will move like this. Okay, so it can move from this point to this point. So it will slowly will come to this point. Once it comes to the right track, otherwise we have track here, right? So example, first of all it starts here, it will move like this. Once it moves to the right track, then this is the place I want to write, correct? Let's say this is the place I want to write. Then your disk plate will be rotated. So this is actually a rotational point here. So on basis of this rod, so this plate can be rotated. So somehow, so this plate will be rotated. Whenever this plate gets rotated, so now see, slowly this area will come to this point, and the area where you want to write the data, that will come under the tape head. Once it comes, then data will be written, right? So this IO head knows how to write the data once it gets the point. Now here the problems are, first of all, whenever you want to store the data, plate has to be moved, right? Second one, before that your IO head has to be moved. There are two things. You can imagine your IO head like this, disk head. So it is here. Example, it want to go to the last track, that means which is near to the center. So it will go like this. Then it will come to the point. After that, your plate has to be rotated so that appropriate position on the track where you want to write the data is reached. Once it is done for that, so your plate has to be rotated. I am seeing here two important delays. One is, so seek latency. What is seek latency is, so to go to that IO head or disk head which has to go to the right track, for that it takes some time, that is seek latency. Every time there will be a seek latency. Second one, rotational latency. What is rotational latency is, example, once your IO head comes to the right track, example C, this came to the right track. After that, so example, you want to write the data here, such a way address is generated. Typically what will be the address? Plate number, let's say it is plate number 2, and this is, let's say, track number 2, and third one, let's say this is sector, okay, 20th sector, otherwise sector 20. Whenever this address which is received by disk controller, first of all, so this disk controller enables the plate number 2. That means, so it will tell that plate that, my dear plate, be ready, my dear second head, be ready. So it will be enabled. After that, so T2 will be taken, so track number 2. So it knows the distance between track number 1 and track number 2, that circuit. So appropriately it will calculate the time, and for that time this IO head will be moved. That means, so it will be instructed such a way that it will move to desired track. So that details are unnecessary for us, like how can exactly this IO head can go to the right track. So general idea will be like this. So everyone, this IO heads speed, that designers know. Example, let's say it takes half an hour, otherwise 1 hour to travel 1 kilometer. In that way it will have some pace, right? So actually, to reach track number 2 from track number 1, so which is after all millimeter distance, then we can easily guess, like the designers guess that, so it is taking 1 hour for 1 kilometer. So for 1 millimeter, how much time it will take? They calculate it and they will ask. Otherwise, this disk controller asks this IO head, my dear IO head, we know to reach 5 millimeter, otherwise 1 millimeter, you have to move your IO head for 1 millisecond of time. In that way, if this 1 millisecond of time, if the IO head is moved, then it will come to the right track. Once you reach right track, otherwise IO head reaches the right track, also known as disk head, then, but this is not the place I want to write. I want to write here because it is sector number 20. Same thing. Now, so always, we can assume like this. So this is, your track is addressed like this: sector 0, sector 1, sector 2, sector 3, sector 4, so on. This is your sector number, let's say 20. So sector number 20 is the place I want to write my data. For that, your disk has to be rotated. That means plate has to be rotated almost, it is half rotation, correct? Again, disk controller knows where is the sector number, and to reach that sector number, otherwise the sector number has to come to this point. For that, how long we have to rotate the plate, that details are known to disk controller. So using that, disk controller initiates rotation. That means this is actually rotational latency. So finally it takes some time. These are all mechanical delays. Because of that, so to store your data in your disk, it takes a lot of time. Otherwise, main memory, that's why it takes only nanoseconds of time. It is taking millisecond of time. If these two delays are not there, then even it takes milliseconds of time. But actually these are the essential delays in this disk. So that takes milliseconds of time, you should remember. Here we'll see one more important point, that is, so this IO head, there are multiple IO heads, right? Otherwise disk heads, only one can be active at a time. That means, so if this is active, this cannot be active. So current technology does not support it. So at this moment, let's say we blindly follow it. So we don't require the reasons also, however. So whenever one IO head is active at a time, so though you have multiple plates, either you can write here, otherwise here or here, but you can't write parallelly. That means we can't write data here and here and here at a time, though you have multiple writers, I can say, right? That is one thing you remember. Second one, sir, suddenly I want to write data here, then what to do? This head will be enabled. Already I explained you. One more thing, so we will see to get the advantage of disk, how to save the time is a question. I will tell you some ideas to save the time. Example, if you store your data consecutively in one track, then you can save a lot of time. Why? The reason is, so seek latency is only one time, correct? Example, imagine you have 5 read requests. That means, you are writing 5 times, 5 write requests. Example, you want to write your data 5 times, data number 1, data number 2, data number 3, data number 4, data number 5. Okay, so example, if you store data number 1 in this plate, data number 2 in this plate, after that data number 3 in this plate, in that way if you do it, then what happens is every time there will be seek latency, rotational latency. Rather than that, so if you store all your data consecutively in one track, then what can happen is, so we can save lot of time. How? So first of all, seek latency will be there because we have to come to the right track. After that, there will be a rotation latency to write the first data. From second data onwards, because we are writing consecutively, already your IO head or this head reached the right point, then we are ready. So only the data transfer time, that means this D2 and D3, D4, D5 require just data transfer time. Usually what is data transfer time? Once we reach to the right point, we have to write the data, that is called data transfer time. Typically data transfer time depends on how much data you are writing, and in the worst case if you fill entire track, then that takes typically one rotational latency, correct? So because whenever you're writing the data, your disk has to be rotated, correct? Then only we can write it. Example, you are here, I have written A, then to write B, disk has to be moved, the plate has to be rotated. So finally we don't know exact data transfer time, but we say that this data transfer time will be typically related to your rotational latency. Both are almost same. So rotational latency, right? Now one more thing is, so we can optimize the time by carefully writing the data. How to write the data so that we can optimize it, we will see. Usually when you have data item 1 and data item 2, some data, let's say whatever the units, try to write it in sector number 1, whatever the sector. Example, currently your IO head is pointing to a particular sector, try to write there so that we can reduce lot of time, because no seek latency, correct? Then once it is done, so initially we assume that, let's say your IO head is resting on some safe position where there is no track, nothing. Then to write data number 1, then we will come to a particular track, right? To come to track number 1 or whatever, it takes some seek time, it is millisecond. So try to reduce it. How to reduce it? However, we cannot avoid. Then next time whenever you write the second data, try to write on the same sector if you have space. Then later D3, same sector. After some time what happens, this sector will be filled, right? Then try to write in the next sector. If you write it probably, so there is no seek time from now onwards, correct? For all other data items there is no seek time, only for first data you will have seek time. Then only rotational latency will be there, correct? Because plate has to be rotated to write the data here, here. And one more thing, so your IO head will not be rotated circularly like this, only it will do this linear movement until it reaches the right track. Later plate will be moved so that we can write the data here, we can write the data. That is the best way. So I can say that finally, if you want to write the data closer to, if you want to write the data which is close to other data so that we can retrieve it fast, I can say that is the best thing is write on the same track, and if possible write on the same sector. Now once it is done, let's say you have lot of data but your particular track is completely filled, then what to do? Then if you move your IO head to the next track, again you require seek latency. To escape that, do we have alternative? Yes, that alternative is don't move anything. We have another IO head, right, disk head. So second time, see, example, let's say once you make full round, you will come back to the same position, right? Then here we write the data. That means once this track is full, we try to use this head and we try to start same thing whatever you did here, right? So in that way, example, this is track number 1, this will be the track number 1. In this track number 1 we write the data. Once it is finished, then still you have data, then probably I write in the track number 1 in the third plate. In that way, in every plate first of all I write. After that what happens, your track will be, all the tracks will be filled. Then now move your IO head to second track or next track. Then do the same. Once it is filled, then come here and fill it, the corresponding track. After that fill the corresponding track, so that you can reduce the lot of seek latency. Understand? So that is the goal. Now finally, what I want to say is, if and all if you want to use, you want to keep your data closer logically, that means what is close data here? If data is in same sector I can say they are close because they are related data, right? Some sort of related data. Then only we do that, correct? Now after that, if you have two data items which are on different sectors means what? Somehow they are related. Maybe they belongs to same table, otherwise they belongs to same record. In that way we can imagine. Now if any two data items in this process, if you store on same sector, I can say that they are part of same record, right? Maybe they are part of same field. In that way we can imagine. Now once this entire track is filled, then we are coming to next here, right? Another plate. Then see, this is D1, let's say here this point. Here you are writing some data, let's say that is something D10. What is the relationship between D1 comma D10? Mostly, so D1 and D10 also something somewhat closer, not so closer, but they are closer. Maybe they are part of they are two different records belongs to same table. When it will happen? Example, you have a table, you are storing it in your disk, then see record 1, record 2, record 3, record 4, record 5, in that way you fill, then you will come to this track, right? Then maybe this is record 50 or something. Still, so somewhat we can say they are closer, right? That is what the idea about this disk and how to optimize it. So now we will see one more concept called block. What is block? And you know what is sector, right? Sector is the minimum size unit in the disk. It is fixed. That means its size is fixed by your disk manufacturer. Typically it will be 256 bytes to something like 1024 bytes. We can't change it. Once you purchase a disk, then this will be fixed. Now actually you don't want to do the transfers with respect to sectors. Let's say you are now a DBMS application and you want to deal with the data. Example, you have some data in with you, you want to store it in some logical units. So usually typically that you don't want into that size, you don't want to keep as sector. Okay, then we can fix something else that is called block usually. So what is block? Block is nothing but some set of sectors. Okay, so in such a way, so any application, either DBMS or operating system, will decide its block. So at this moment we focus on DBMS. So your table will be divided into logical blocks and each block size is typically some set of sectors, like 3 sectors, otherwise 4 sectors. It's definitely multiple of sectors. So that is the way your DBMS will be designed, so that from now onwards, whenever I want to access my data, then the data transfer will be block transfers. Okay, so that is what block. From now onwards for us in DBMS, the data transfer, whenever I want to transfer the data from disk to my main memory to access it, I do block transfers. So there is a big story for that. So why block transfer? Why not sector? Why not byte? We will see. First of all, we'll see why not 1 byte. So if you transfer the data in just bytes, like typically we do in a main memory, whenever main memory you have, generally we transfer the data from main memory to registers to add or subtract in bytes, like 4 bytes or 2 bytes. The reason is the arithmetic logic unit, whatever you are using. That example, take adder circuit. Adder circuit is designed such a way that it can add to integers of size 4 bytes, correct? Otherwise maybe 8 bytes. So that's why we do the transfers from main memory to CPU registers in 4 bytes. The same thing if you do here, like 1 byte, otherwise 2 bytes, what happens we'll see. Example, let's say you have a table with some only one field for easy understanding, student ID, and there are some students, 1000 students, and you want to read every student. For that, let's say probably user wrote this query, select star from student. This is called scanning the table. Example, let's say you are scanning the table or you want to access all the table, then what happens in the reality? So really your data is stored in your disk in consecutive sectors, let's say, assume that. Then really, example, let's say the data transfers are allowed only bytes. That means at a time you can access only 1 byte. For that we have a command called fetch. So whenever you call fetch, only 1 byte is transferred. We don't have other option, let's say. Then what happens? So fetch, how many times we have to write this fetch? Probably, example, there are 1000 records in your table. Then you have to write fetch 1000 times, correct? So when you write fetch 1000 times, probably what can happen there? And one more thing. Example, let's say your data is distributed over all the places. We don't know where you are storing the data. So completely randomly you distributed. In that environment, what happens is, first of all, for first byte, prepare the head. So you need seek time milliseconds. After that, to go to the right byte, example, the first byte is here. To come here, rotational latency, millisecond, right? After that, data transfer time, let's say something around millisecond will take. So 3 millisecond is required, right? So otherwise we say that entire thing is, one data transfer. Let's use a unit called B. Okay, so we require B time, otherwise millisecond. How many such milliseconds we have to have? One is for this one. For second one, again we have to use this instruction fetch, because at a time we are able to access only 1 byte. If that is the reason, then to access 1000 bytes, all 1000 records which are 1000 bytes, let's say assumption, then you require 1000 fetch operations. Each takes seek time, rotational time, everything. Then it takes 1000 milliseconds. So that is definitely, it is not a good idea, right? So no one prefers it. That is the very bad idea we have. It takes 1 second of time to just after all fetch 1000 records. So I can give one more analogy for this one. Usually I give it. So it is like constructing one building with 100 floors. Let's say your father is engineer. Let's say he has constructed one building like this. Okay. So this is kitchen on 100 floor, and your dining hall is here. Let's say dining hall, this one, it is at first floor. Now imagine this situation. Let's say your friend, imaginary friend Raju, came to your house to just for having lunch with you, and he's damn hungry and he wants food immediately. Then see the situation. Let's say your kitchen is here and your mom is expert in making laddus. Let's say something, we take something, laddus, and now today for lunch you are just giving him laddus. Then the first question you ask, because now he want to eat lot of laddus, it is like data transfer. So let's say laddu eating is nothing but for Raju data transfer. So how many laddus he want to eat? Let's say you don't have, let's say, clue. You don't have any clue. Then how you do it? Probably one technique which you are using here is fetching 1 byte, right? If you fetch 1 byte here, then from your kitchen you are going to fetch only one laddu, which is, let's say, very small in the size, 1 byte, right? So when you only fetch one laddu from kitchen, how much time you will be taking? Let's say, because there are 100 floors, there is no lift, then you take 1 hour. So both are similar, fetching 1 byte and fetching one laddu from kitchen, because this is your dining hall and this is kitchen and there is a lot of delay. So after 1 hour you fetch one laddu and you give to your Raju. Then Raju will eat immediately, because he is like a CPU. His data transfer rates, otherwise his processing time is nanosecond. That is a problem. Since disk is electromechanical device, since you are traveling 100 floors and coming back, you took 1 hour. But to swallow that laddu, so Raju takes, because he is damn hungry also, he will take only 1 nanosecond. After 1 nanosecond, he will ask one more laddu. Like, asking, example, let's say once you fetch the first record, you want to fetch second record. Because what is your program? Your program is accessing all the records, let's say. For that, here, Raju's program is, today he want to eat lot of laddus, minimum 100 laddus. Then 100 times you will be busy getting the laddus, then 100 into 1 hour, because every time you are getting only one laddu. So that will be definitely bad idea. In the same way, if you transfer the data from secondary memory to primary memory in bytes, also a bad idea. So no one will do. Just I am giving the intuition. So why usually people say data transfers are blocks. That's why finally every application program usually do the data transfer from, usually in in blocks rather than bytes. Correct? Now here you tell me for Raju, let's say Raju should not be angry. He should be very happy after eating laddus. For that, what should be your strategy? Think about it. Do you bring only one laddu per one iteration? Don't do that. So though you don't know how much, but don't ask me, don't ask Raju, Raju, how many laddus you eat? It will be offensive. So you should, for a guest, you should not ask that question, right? So that's why the best thing is assume something like, guess usually how many laddus you eat. Raju also a similar person, correct? Then if you eat, let's say 15 laddus, then you also bring same order of laddus, that means 10 to 15. So what you do is guess that Raju takes only 15 laddus and Bring 15 laddus and don't put everything in his plate. He might be little bit shy, otherwise his capacity is only 2 laddus. Who knows? Anything can happen. But tendency is he might eat 15 laddus. That's why you brought 15 into the dining hall and keep somewhere, and because he asked only one laddu, you give him one laddu. Once he eat that laddu, definitely he will eat one more, right? He will ask. Then he will write one more instruction to you. That is, my dear friend, give me one laddu. Then this time you will not have any seek latency and rotational latency, because all the similar data, otherwise all relevant data, you already brought it and you give him one more. In that way 14 times there will not be any problem, correct? In the same way, example, let's say when your let's say one block size equal to, let's say, 4096 bytes, that is assumption, right? Then you have written a program to fetch 4096 bytes, let's say. Okay, so let's say your program is fetching 4096 bytes. Then how that program will work? First time you will try to fetch one byte, right? First byte. At that time, though you are asking one byte, then block will be transferred later on. Then for second byte, third byte, fourth byte, you don't require to go to secondary memory. Such a way your organization is fixed. That means this is an optimization from organization side. Okay, CO. So to fetch 4096 bytes, if block size is 4096 bytes, then after all it takes only one seek time and one rotational time and one data transfer time. Okay, so this entire thing, let's say we say, one block transfer time, correct? So it only takes one block transfer of time. Example, your program wants to fetch some 4 blocks. How much time it will take? For that, first time, whenever you try to fetch the first byte from the first block in your data, for that first block will be transferred. Second time onwards we can get it in main memory. Then after that, so second block, after the third block, for every block only one block transfer will be so it will happen, and for 4 block transfers it will be only 4 block transfers, 4 millisecond, right? So that will be the optimization from your organization, remember it. Now we'll see how this disk can be used to store the data. So let's say this is your disk and these are all the various blocks you have in the disk. So don't worry about which track they belongs to, which sector they belongs to. So they are all, let's say, all the blocks of the disk. So now we know that in a hardware perspective there will be a disk controller. Forget about it, right? That means finally disk controller is going to decide where is the block, everything. Now whatever the software we use, that should consult this disk controller, correct? So through CPU, that is architecture, right? So that means it is hardware. So don't worry about that hardware. Already I told you that CPU and disk controller should be communicated to actually store the data. Now we'll see software perspective. In the software perspective, what are the things we have? One is disk space manager, which is part of DBMS. So especially low level software, and buffer manager. This is one more module. We will see the purpose of this buffer manager. Usually whenever you have lot of functionality, we divide the functionality into multiple parts and we say layers, right? This is one layer, disk space manager. This is another layer, and some other software. What is the other software in DBMS? Transaction concurrency management, otherwise recovery management. There are a lot of things which DBMS has to do. Then there will be lot of modules. Let's say these are all other modules. Now let's say we focus on how data will be created first of all. Example, let's say this is your employee table, so which is stored in some file called employee file. So logically your data looks like this, correct? 1A, 2B, 3C, 5D, 4E, 6F. Now, so this other software, whatever is going to create this data, it will imagine its data as this kind of unit that is called page actually. Okay, so from now onwards we use either page or block interchangeably. Both are actually almost same, but what is page is, so your DBMS divides your tables into logically some units. They are called pages. Now typically page size is exactly equivalent to block size. Okay, in that way page and block are same. That's why I use page and block interchangeably. Now block is about disk, some set of sectors, correct? So it is related to disk, and page is related to your table. Now let's say you have some multiple pages, then the question is, so this software is thinking how to store them in the disk. For that, this software will consult Mr. Disk Space Manager. This Disk Space Manager, of course, is again part of DBMS. He will know how to communicate with, for that he will have instructions such a way that how to communicate with this disk controller, and otherwise how to communicate with disk. Some students ask here one interesting question, sir, actually CPU communicates with, right? So CPU is common, whatever the software you execute, finally CPU executes it, right? Now that's why ignore that part. So we are coming to one more abstraction, that is this CPU has to run some software to communicate with disk controller, right? Someone has to told CPU that, my dear CPU, please communicate with this controller. That is through software. So someone has to write the software even to do even inch of work. That's why this disk space manager will have code. That code will ask this disk controller to store the data. Now this disk space manager will take care of all these things, like how data, where data is going to be stored, right? Everything. Your disk space manager remembers everything, like so which blocks are used for the table. Now try to understand the difference between these pages and this imagination and this imagination. So disk space manager is responsible of storing your this logical data into actual blocks. Example, let's say we'll ask, my dear disk space manager, I have a logical page P1, its logical address is P1. Okay, so this is page address P1. Please store it in some real world space or disk. Then this disk space manager will be executed. It will communicate with that disk controller through the code, and it will get some block, and in that block, so it will store the data, like example 1A comma 2B. Now, so your disk space manager remembers this mapping. For you it is page number 1. For disk space manager it is B1. From now onwards, whenever you ask, from now onwards we have to ask only disk space manager about your data. My dear disk space manager, I want P1. Then he will go and get data from P1, because he knows the mapping between your logical page and physical block. That's it. Similarly, 3C5D, you just give to him, he will take care of the data space, like the disk space, how much we have, everything. So that's why it is called disk space manager in that way. And one more thing, there are two kinds of DBMS softwares. Some softwares will again further consult operating system in between before storing the data. There are two things. So some softwares consult operating system and they will depend on operating system to store the data. That means, so this is your DBMS and this is your operating system, this is your hard disk. And some DBMS, there are some DBMS, of course, but only minority. They say like that, my dear operating system, I take your files. That means, I use you, otherwise I use your softwares to store my data into disk like every application program. That is one way. Second one, there are some other DBMS softwares, they don't depend on operating system and they directly store their data. So there are two methods possible. One is directly consulting, second one consulting through operating system. So actually we know that, we will study that in detail in operating system. Operating system also knows how to store the data in this secondary memory or disk. OS has software, they are called drivers, right? So using the drivers, it will store the data, whenever. So actually you do that. Example, if you write a C program and if you submit, if you save in your computer through some operating system, that operating system is going to store it in real disk, right? So that is actually OS task, but we should not depend on operating system. Our OS can do it, but don't depend. The reason, if you write a code, if you have DBMS, generally if you design a DBMS which is not depending on operating system, it is directly storing the data, then you will have control on the data. That means you will know where to store the data, when to store, and you can do lot of optimizations. Example, better things about your data. Example, see this situation. When can I use this direct communication? I have some employee table with 3 pages, P1, P2, P3. I know that these 3 are related and they are going to be fetched immediately. That means, after P1 definitely P2 is to be accessed. After that P3 should be accessed because they are all related information. Then what I do is I store P1, P2, P3 pages in consecutive blocks. So we know the advantage of consecutive blocks. Whenever you store your data in consecutive blocks, then the access time will be less if you compare to storing that random. But if you consult operating system, there is a danger that because OS cannot know whether you have given similar information or related information or not, then OS will do its own strategies probably that might not work for your data. That's why we as a DBMS, it's a huge database, right? And you have lot of interest in your data. That means you want to retrieve the data very effectively. For that, don't depend on operating system. Second thing, it will become portable. If you write code which depends on operating system, that means based on OS properties, if you write your DBMS, then what happens? Then tomorrow, if you want to install the DBMS which is designed with Microsoft OS, let's say, then there is a danger. Now it will not be portable, right? So this DBMS which is written with based on this operating system Microsoft, which is using Microsoft features to store the data, then if you run that in other operating systems, that might not work. So there are a lot of problems, correct? So that's why usually DBMS is a huge software, so that will do its own things on its own. That means it will not depend on operating system. Majority of the DBMS will do that. Okay, so what is the final thing we want? We want to get our own data, I mean our own blocks. That means this is disk. We directly consult with disk controller, right, rather than using the operating system code. That's it. That is what I want to say, right? So now we'll come back. So we understand disk space manager. What is the responsibility of that? So this disk space manager is going to solve a problem called where your data is stored. So now let's say we are other software, right? So I mean we are also part of DBMS, but disk space manager also part of the DBMS, but the other software will focus on creating the data and manipulating the data, but we don't require, being here, we don't require to focus on how data will be stored, right? Example, at any time whenever I want to get page number 5, then I can get it. So just consult disk space manager, he will give you, right? Now we'll see the role of buffer manager. Sometimes we have to consult buffer manager, so it is going to help you a lot. How it helps, we'll see. Example, let's say this buffer manager is given some buffer in the main memory. That means it can use this buffer. This is called buffer. The buffer is nothing but some set of pages. So that means it can hold some set of pages, I say. Initially, let's say your buffer manager, whenever your program begins, irrespective of what your program does, it will fetch some pages. That means page number 1, I'm just showing page number 1, but logically that page number, physically that page number 1 is block number 1. So it will try to fetch 3 pages. For us it is pages, but actually they are blocks. Let's say B1, B2, B3 contains that 3 pages, P1, P2, P3. It will prefetch it. What is the advantage of that, we will see. Let's say in your program you want to scan all the records of your table. That means you have written a query which should retrieve all the tuples of the table. Then what happens? What you want to fetch B1, B2, maybe let's say this is 4e, 6, f, which is stored in B3. Then since it already prefetched, then you just consult buffer manager. My dear buffer manager, so I would like to fetch page number 1 from the disk. Why? Because I want to fetch not only page number 1, I want to fetch all the pages one by one. I will ask you. Then whenever you consult buffer manager, what it will do is it will say, don't worry, already I prefetched it, take it. So it takes 0 time for you, correct? Then you can process it whatever you want. Example, you want to observe every record, right? Maybe then you can do it. So it won't take lot of time. Imagine, let's say you are scanning this table size is very big. Let's say it has, let's say 100 blocks or 100 pages. So when your table has 100 pages, then you want to scan that all 100 pages. I don't know the reason. Then probably you will be asking buffer manager after 3rd page, 4th page. My dear buffer manager, I want 4th page. What do you do? Since it is not there in this buffer, what it might do is, so it will decide. That means what it will do is some block, otherwise some page, I can say from now onwards, some page will be replaced. That means, what it will do is it will fetch some extra pages, like this time page number 4, let's say it is stored in B4, B5, B6. I assume that, let's say this is page 4, this is page 5, this is page 6. Now again it will fetch P4, P5, P6 maybe. So that this time again you get advantage. How? So next from now onwards, though you asked P4, it brought P4 and P5 and P6, right? Then P4 is available, and for P5 you don't require to go to disk again, and for P6 you don't require to go for disk. In that way, using prefetching idea, it will save your time. That is one thing. There are some other lot of works it will do. So it will do page replacement. That means, so it has some collection of pages, right? So if your all buffer pool is filled like this, just now already we discussed it, when your buffer pool is full, then it will guess that this P1, page number 1, is not really required at any time. In that way, somehow it will guess that page number 1 is useless, and next time when you ask page number 4, then it will fetch page number 4 here, and page 1 is removed from this buffer pool. Understand? So you get advantage of this buffer manager when you repeatedly request for blocks. Example, one block is accessed 100 times. Then what your buffer manager will do is, it will say that P1 is very precious. It will somehow remember like this. Oh, lot of people. Assume that, let's say this employee table is accessed by hundreds of people, and especially the first page people are accessing. Then what it will do is, wherever the P1 is located in block number 1, right? So it will bring that entire block number 1 in buffer, and it never removes it. Somehow it will learn it using the strategies. So from now onwards, any program comes and want to fetch that B1, then they will always get into main memory, then they can escape seek time. So finally the summary is like this. So buffer manager understands what are the frequent pages people are accessing. Then that pages from the disk it will prefetch, and it will hold in the buffer. For them, definitely you don't require any disk transfer. Correct? So that is the way your buffer manager plays very important role. Now what is disk space manager is, disk space manager will abstract the disk storage everything, and whatever the logical page you have, if you give to disk space manager, that disk space manager is going to store it. So these two are independent software units, and this buffer manager might communicate sometimes with disk space manager. Why? Example, let's say one program want to access block number 1, which is nothing but for us page number 1. Okay, so assume that, let's say that is not available at this moment, but we ask buffer manager, my dear buffer manager, did you store it in your buffer P1? I want P1 actually. Then that buffer manager says that, oh, I'm sorry, in this my entire buffer there is no page number 1. Then it will go to disk space manager, and it asks buffer manager communicates with disk manager, my dear disk space manager, please fetch P1 immediately because I want it. So immediately disk space manager converts that page number 1 to corresponding block, because he knows where it is, and he will fetch and he will keep B1. Then immediately that buffer manager, once this entire thing is done, that buffer manager will come to us and says, you asked P1, right? Now yeah, please take it. What do you want to do? You want to do the processing? Yes, you can do in the main memory. In that way, so this main memory buffer will be used. Sir, can we directly do processing in secondary memory? No, you cannot do, because to do processing, definitely we have to do in main memory only. That is the way your computers are designed. So your computers are not designed such a way that the arithmetic or whatever can be done in secondary memory. Even we are not directly connected, I can say, right? So we have to fetch the data first of all to main memory, then later we have to access it like whatever the way you want. Example, generally what do you want to do with the data? I want to do with the data, like I want to see the salaries of employees. Otherwise I want to see the name of the employees. For that, whatever you fetch the data to main memory. Here example, let's say once you fetch page number 1, that is 1 comma A, 2 comma B, then you process every record one by one through your programming, right? So that is the concept of accessing the data.